solving more exponential and logarithmic equations. Some of these are going to be in slightly more complicated form than what we've seen so far, but we're going to have some techniques that will make these work in a very straightforward manner for us as we conclude this lesson. So we're going to get to the stage where we might see something like this. The log of x plus the log of x plus 3 equals 1. Or the log of x squared minus 1 minus the log of x plus 1 equals 2. And we're going to use our properties, all the different properties that we saw in our last class. Be familiar with them. Our techniques for rewriting an exponential as a log or a logarithmic as an exponential. All those techniques are going to come into play for what we do today. Now, to get things started, we're going to use a property that we used at the beginning in section 4.1, the uniqueness property for exponentials, when we had b to the m equals b to the n, which would tell us that m has to equal n. Well, there's a similar property that works for logs. If the log base b of m equals the log base b of n, then m equals n. So that uniqueness property works very nicely both for exponentials and for logarithms. Obviously, your logarithms have to be of the same base for this to work, so one extra proviso. So if we work with a problem like this, log of 2x minus 3 equals log of 3, this is a perfect example of the uniqueness property. We can go very quickly and say, hey, works perfectly with the structure that we see in the little box up there. We can say that 2x minus 3 equals 3, 2x equals 6 with just a little basic algebra, and that x equals 3. And so that's the kind of stuff that we'll work through in this lesson. I'm not going to worry about these pages that you see down here and just a couple other examples. Those are just for you to work at your own pace when you have the opportunity. But let's go into some solving situations. Again, we have slightly more complicated logarithmic expressions than we did before, but we can work these. And here's the technique. First things first, whenever you see multiple log or ln statements on one side, consolidate them, convert them into one single logarithm or ln expression. In so doing, if you wind up with your uniqueness property, you'll have the log of something equals the log of something else, or the ln of something equals the ln of something else. You can set those pieces equal to each other and solve using our uniqueness property. If not, we'll just take some further steps and do other techniques, either rewrite, and so on and so forth, to go ahead and build a solution. What we'll find in this is some of the things that we're going to work with, we might have to solve some type of quadratic or a linear equation, and we'll come up with some possible answers. So I'm going to say over here, solve the resulting quadratic or linear equation to get possible answers. And then you should remember from Algebra 2 last year, when you did this type of solving, you had to check your possible answers back into the original equation. And if there's any circumstance where you're being asked not to take the log of a number that is not positive, you need to reject that potential solution value. Recall, you can only take a log of a positive number. So if any of your possible solutions, when you go back to the original equation, they require you to violate that rule. In other words, taking a number, log of a number that is not positive, you need to wipe out that solution. So here we go. Let's start working through these problems. ln of x minus 1 plus the ln of 6 equals the ln of 3x. Well, I would like to use my uniqueness property. If I could make this thing on the left a consolidated log statement. And by the way, what do I notice? Hey, it's an ln of something plus an ln of something else. That talks to me of the product property. Please make sure, go back to your notes from the prior class, section 4.4. You know all the logarithm properties that you see on the first page of that notes. In any case, this is a product property, so the log of, I could multiply this thing, x minus 1 times 6. I'll write it out. I'll use parentheses and some brackets. So I just need to distribute the 6 to the x minus 1. I'm going to have the ln of 6x minus 6 equals the ln of 3x. Uniqueness property worked great. 6x minus 6 equals 3x. Do a little bit of algebra. I'm going to add x on this side, subtracts 3x from the right side. I'll have 6x minus 3x, or 3x equals 6, and x equals 2. That's my possible solution. The last piece with my possible solution, go back to the original equation. Log of, wait, when I put in a 2, I'd be taking the log of 1. That's fine. ln of 6, no problem. When x equals 2, I'm still taking the ln of 6. And over here, when x equals 2, I'd be taking the ln of 6. Every ln that I'm being asked to check with a value of x equal to 2 in the original equation is a legit number. This is a good solution. I'll accept it. All right, next problem. A little bit different. I got a log on one side. I have a constant on the other. But still, same technique. Take a look here. Log. And hopefully you can recognize that I got the product property again, so I'm going to go a little bit quicker on this one. I can multiply x minus 7 times 3, and this will become the log of 3x minus 21 equals 2. Now, I don't have a uniqueness property here. What can I do, however? I can rewrite as an exponential form. Remember, if it helps you on rewriting, hey, that's log base 10 when you see log by itself. And so if I rewrite, I'm going to have 10 squared equals 3x minus 21. Remember, the answer to a logarithm is the power in an exponential. The thing you take a log of is the answer to an exponential. So I have 10 squared equals 3x minus 21. 100 equals 3x minus 21. 121 equals 3x. X equals 121 over 3. And if I do that for a decimal, that's going to be about 40.3. Do I look at this original answer in the first equation, the initial equation? I sure do. When I put 40.3 in there for x, I'll be taking the log of 33.3. Totally legit. All my other logs are fine. This is a good, acceptable solution. All right, let's keep plugging our way along. Hey, this one looks very, very similar to, our first problem. Looks like I got a consolidated log that I could build. In this case, it looks like I'm using the quotient property. I'm going to have the log of x plus 14 over x equals the log of x plus 6. Quotient property on the left side. What's this telling me? Well, it's telling me that I have uniqueness property at play. I can say x plus 14 over x equals x plus 6. To solve this, I'm going to multiply each side by x. X plus 14 equals x times x plus 6. X plus 14 equals x squared plus 6x. All right, hey, I got a quadratic. What will I do? I'm going to bring everything over to one side. X squared, 0 equals x squared. 6x minus x plus 5x minus 14. Next, what do? Factor. 0 equals, well, x squared plus 5x minus 14 factors as x plus 7, x minus 2, offering solutions at x equals negative 7 and x equals 2. These are my possible solutions. I'm going to go back to the original equation. Let's use x equal 2 real quick. Log of 2 plus 14, log of 16, great. Log of 2, no problem. Log of 2 plus 6, log of 8, great. X equal 2, I'm going to accept. X equal negative 7, well, it works here. Negative 7 plus 14, I'd be taking the log of 7, no problem. But hey, as soon as I get to this second one, I'm going to be taking the log of negative 7. I need to reject that. My final solution is nothing more than x equals 2. Remember, you only have to fail one logarithm statement. As soon as you fail one of them, that'll let you know that you can reject a possible solution. All right. Now, let's look at something in a different light. Log base 4 of x minus 10 equals 2. Well, this one's sitting right in front of us, and it's something that we've done before. Think, rewrite. I could do this as 4 squared equals x minus 10. 4 squared equals x minus 10. Remember, answer to a logarithm becomes a power, base, exponential base. What I was taking the logarithm of becomes the answer. 4 squared happens to be 16. 16 equals x minus 10. X equals 26. By the way, just to show this to you, I could have done this in a couple of places, but look at this. Log base 4 of x minus 10, I'll leave that over here. 2 is equal to the log base 4 of what? This is another way we could do this problem. It's not preferred, but it's another way. If you like to do things of this nature, don't hesitate to do it. Well, it turns out that the log base 4 of 16 happens to equal 2. So I could have gotten to the stage where I would have had the log base 4 of x minus 10. 2 could also be written as what? The log base 4 of 16. Stare it down for a moment. Just make sure 2 log base 4 of 16 that you're comfortable with they're the same thing. They absolutely positively are. What would that tell me? Gee whiz, I could use my uniqueness property if I went about it this way. X minus 10 equal 16 and x equals 26 comes out. So different ways to kind of skin some of these, take advantage of it. Don't be afraid. Whatever technique you feel most comfortable with, go for it. There are multiple ways to get at these. All right, let's do some more work. General method for solving exponentials. We've talked about this in prior lessons, but here's another approach we can take. When you see exponentials, don't be afraid to take the log of each side, particularly when what? When you see, and it's true with all these problems, your variable is living in the exponent. When you take the log of something like 8x or e to the x minus 1, the power law is going to be right behind you. And remember, with the power law, the power property for our logarithms, you can drag that power in front. Let's look at a couple of these examples. I'm going to save, just in purposes of working through these, I'm not going to go ahead and actually calculate through all our log numbers. I'll let you work that on the calculator. But we'll go ahead and get most of these set up, just again to save some time. Well, first one, I'm going to do the log of 8 to the x equals the log of 792. The beautiful thing about doing this is what happens with the power property. The x drags out front. X, the log of 8 times the log of 8 equals the log of 792. X is nothing more than the log of 792 over the log of 8. And I can get that straight from my calculator. 2 to the negative x equals negative 0.045. Same thing, log of 2 to the negative x equals the log of 0.045. The power property, negative x times the log of 2 equals the log of 0.045. Divide each side by log of 2. Negative x equals the log of 0.045 over the log of 2. I don't want to know what negative x is, I want to know what x is. X is equal to negative log of 0.045 over log of 2. So you do this. I'll go ahead and just do this one just so you can kind of see the mechanic on it. I'm going to take the log of 0.045. I'm going to divide that by the log of 2. And then I'm going to take that answer and change its sign. So my answer will become positive 4.47. And there's your process. All right, let's do a couple more. E to the x minus 1 equals 15. Well, again, remember, what can we say if we do a rewrite of this? Remember, the answer to an exponential is the input, what you take the log of. Base e, I must have an ln of 15 equals the power x minus 1. This is a perfect rewrite. Logarithmic form, exponential form. I want to solve for x. ln of 15 plus 1 equals x. And again, you could run that through your calculator. 2 to the x plus 1 power equals 30. All right, log 2 to the x plus 1 power equals the log of 30. Power, x plus 1, notice parentheses, times the log of 2 equals the log of 30. X plus 1 equals the log of 30 over the log of 2. Just kind of follow my steps. Pause the video if you need to. I want to solve not for x plus 1, but for x. So x equals, and we'll get this number, this first piece, log of 30 over log of 2 from our calculator. We'll subtract 1, and we'll have a clean final answer. So again, remember, if the variable you're looking for is in an exponent, take a log. Let the power property help you out. So I'm going to move around a couple different locations for the remaining problems. Let's start down at the bottom one. 10 times e to the 2x equals 400. This is similar to one of the problems that we saw in our notes from the prior class. And I always said when you have an exponential, make sure you clear out any coefficients that are in front of that exponential. In this case, I want to clear out that 10. I do so by dividing each side by 10. E to the 2x equals 400 over 10. E to the 2x equals 40. What can I do next? Well, tell you what. Let's take an ln. ln of e to the 2x equals the ln of 40. Power principle tells us what? Power property, 2x times the ln of e. I'm going to put parentheses around the ln of e equals the ln of 40. What do you know about the ln of e? Well, ln of e is the same as log base e of e. And remember, log base b of b, that's one of the principles from the last note section, one of the log properties, that's equal to 1. So I wind up with 2x equals the ln of 40, and x is nothing more than 1/2 times the ln of 40. And again, work your way through calculator. 10 to the power x over 2 equals 1/2. Well, here we had e to a power, and we did an ln. Here we have 10. Why don't we do log base 10, or log of 10 to the x over 2 power equals the log of 1/2. What's the nice thing that happens? Power property, x over 2 times the log of 10 equals the log of, I'm just going to change this to 0.5 just to help myself calculator-wise. What's the log of 10? Log base 10 of 10, that's 1. X over 2 equals the log of 0.5. And x is nothing more than 2 times whatever our calculator tells us the log of 0.5 is. Okay. Let's work over here. Log of x minus 2 plus 3 equals the log of 5x minus 7. Hey, this one, I got logs on each side. I think the uniqueness property. I notice a plus sign between these two individual logs. Product property, sounds like a good candidate. X minus 2 times 3 happens to be 3x minus 6. So I'm going to have the log of 3x minus 6 equals the log of 5x minus 7. Uniqueness property tells me 3x minus 6 equals 5x minus 7. I'm going to add 7 over here. 3x plus 1 equals 5x. I'm going to subtract 3x. 1 equals 5x minus 3x, or 2x. X equals 1/2. This is my possible solution. What do I need to do with it? Go back to the original equation. When I take the log of 1/2 minus 2, I'm taking the log of negative 1.5. I can't do that. I need to reject this, and since it's our only possible solution, there's no solution to this equation. Okay, onward and upward. Let's take a look up here. Log base 3 of x plus log base 3 of x plus 2 equals log base 3 of 8. I'm hoping for a uniqueness property here. I got logs on each side. Consolidate the left-hand side. You got adding 2 logs. Product property, x times x plus 2 is what I'm going to have, which becomes 2x plus 2, x squared plus 2, x squared plus 2x. Get my algebra right, sorry about that. So I'm going to have the log base 3 of x squared plus 2x equals the log base 3 of 8. What's that going to buy me? Uniqueness property, x squared plus 2x equals 8. X squared plus 2x minus 8 equals 0. I'm going to go over here just so I got a little bit more real estate. X plus 4, x minus 2 equal 0. Possible solutions, x equal negative 4, x equal positive 2. Original equation. Hey, negative 4 certainly isn't going to work. Reject. X equals 2. Yep, log of 2. I'd be taking a log of 4 here. This is perfect. I can accept x equals 2. And there's my final answer. All right, 2 more to go. Let's do number 3. Log of x minus the log base 2 of x minus 2 equals 3. Quotient property. Log base 2 x over x minus 2 equals 3. Not quite as pretty as I like, but let's see what we can do. I can rewrite this as 2 cubed equal x over x minus 2. That's a perfect rewrite. 2 to the third power equals x over x minus 2. 8 equals x over x minus 2. And now to solve, I'll cross multiply. 8x minus 16 equals x. 7x equals 16. And x equals 16 over 7, which is just a little bit bigger than 2. Check this. Log of 16 over 7. Sure, no problem. I can take that. Log of 16 over 7 minus 2. We said 16 over 7 is a little bit bigger than 2. 16 over 7 minus 2 is a positive number. This is a good solution, and I can accept it. Our last problem lives up top. Negative 2 ln of x plus 1 plus 7 equals 7. Well, I'm going to subtract 7 from each side. Negative 2, the ln of x plus 1 equals 0. Well, hey, if something times something equals 0, what's that telling me? It's telling me that the ln of x plus 1 has to equal 0. No choice. How do I get a solution out of this? Well, remember, ln is the same as log base e of x plus 1 equals 0. A rewrite would tell me that e to the 0 equals x plus 1. E to the 0, anything to the 0 is always 1. 1 equals x plus 1. And that's telling me that my solution is x equals 0. Check x equals 0 back to the original equation. Can I take the log of 0 plus 1? Sure, that's a positive number. This is a good, acceptable solution. So the bottom line with all these problems is be comfortable, know your properties, know how to work with your properties, know how to rewrite. The ability to rewrite these things frees you up so much that you can work your way through all these types of problems. That's it for solving log.